is essentially a measure of mass, essentially volume. So, and 2 carats, you think it's twice as big. Oh, it'll be twice as tall, twice as wide, twice as everything. But it isn't. A 2 carat diamond is only marginally larger in terms of diameter than a 1 carat. If you want to get a diamond that genuinely looks twice as large in terms of its height and its radius, it's an 8 carat, and it costs at least 8 times as much. And there's other interesting things here about how why you can't have like a 12-foot tall person. It's because as you get larger, say for example, if you double your height, the bones, for example, in your legs, the strength of them is related to their area, and the area goes to square. So if you double your height, your legs will get 4 times as strong. However, your mass, because it goes as the cube, gets 16 times stronger. So you have a problem. Double your height, you get 16 times heavier, but your bones are only 4 times heavier. Well, obviously that's wrong. It shouldn't be 16, it should be 8. So yeah, if you double your height, you become 8 times heavier, but your bones are only 4 times heavier. So that's why you can't have like a 12-foot tall person. And if you look at an elephant, like their dimensions are totally different. Their legs are far thicker than ours, for example. Okay, so this hopefully is the rough understanding that will get us through the error analysis of Euler's method. Now here's so it's okay. You say that some function is of order g of x if it's less than or equal to a multiple of it. Roughly, what will get you through is that f is of order g if f is a multiple of g. That's what will do us. Okay. Now all this is background for us to analyze the error in the Euler method, because remember, like, we're at level 8 here. We're not just using algorithms. We want to know how good they are. It's no good just us doing some calculations if the errors are very, very large. We have to be able to guarantee that the errors are very, very small. And you can't just make the step size smaller and smaller and smaller, because that comes with a cost as well. Okay. So where are we? Power series. Right. How does a calculator work? This is a question like, how does VBA calculate the sine of a half? Similar problem. How the hell did they do that? The thing is that addition and multiplication are fairly easy to program, but how about finding, for example, the log of 2? No calculator, because it's a finite machine, can calculate log 2 because it's infinitely many decimals. So calculators are using approximations. Here we show some ways that they might do that. Okay. Now we're going into another topic again, but we need to do this to be able to analyze our errors. Right, so what are we going to do? So what we're going to do here is if we're interested in log of 2, we're going to come up with a very, very rough approximation. And how we're going to do it is we're going to start at a point we know about. You should know that log of 1 is equal to 0. And you should also know how to find the slope of the tangent to a smooth curve. This is smooth, so close to 1, it is approximately equal to its tangent. So the line that it looks like is the tangent. That's what a tangent is. And what we could do is we can use this tangent, just as we did with Euler's method just a moment ago, to approximate the log of 2. So, and actually I might just keep the notation. No, I need a different notation. So here we have this height here. It's the log of 2. And I want to approximate it using this. What am I going to call this? Well, how about I call this thing maybe t of x, t for tangent. So this thing here is t of 2. Okay, hopefully there's no one coming in here. No. Right, so we have a point, we need to get a slope. You really, really do need to know at this stage how do you find the slope of a tangent. that should be an automatic question. The slope of a tangent to a curve y equal to f of x, in this case log of x, you differentiate. So the slope at any point is given by dy dx. Now log of x is not too difficult to differentiate in terms of it's in the tables, it's 1 over x. And we want to evaluate this, we're interested in the slope of x equal to 1. So we substitute in x equal to 1. And you get 1 over 1, which is 1. So we have a point 1, 0 and a slope 1. There's something a bit gnarly about my drawing, but oh yeah, it's okay. It's okay. So what we have is y minus y1. So the y coordinate we have that we know about is 0 is equal to the slope, which is 1, x minus x1, which is 1. And then we can just multiply this out, and we get that the tangent, so the tangent of x, is equal to x minus 1. Now the thing I was worried about, by the way, was that when you write a line in the form y to mx plus c, the c is where it cuts the y-axis, and I'm looking at this and I'm going, hang on a minute, it's not cutting at minus 1, but actually if you look at the scale, I think this is only 0.5, so actually it probably should go through minus a half, but there's no problem, So what we have is for points near x equal to 1, now obviously this is actually accurate up to a certain point. I'd say looks something like maybe this point here, which is 1.2. So maybe we might do a little demonstration. So assuming that the calculator is doing things correctly, look at this point here. There's not much between the two of them. So log of 1.2 is approximately, now the calculator is doing things obviously a little bit more sophisticated than this. But now it is given an approximation, but I just want to look at an approximation anyway to it. So this is approximately 0.1823. Now what we've shown here by finding the tangent is that certainly for points close to x equals 1, the red thing, which is t of x, and this thing, which is log of x, they're approximately equal. And t of x is x minus 1. So what you have is that for points close to x equal to 1, log of x is approximately x minus 1. And if you look at x minus 1 at 1.2, which is obviously the thing we're talking about, x minus 1 evaluated at x equal to 1.2 is 1.2 minus 1, which is 0.2. And there's not a whole massive difference between them. We may as well talk about error at this point. So to calculate the error in approximation, you look at the error, which is the difference between these two, which is approximately, I'll just do it, 0.2 minus 0.1823. Error divided by the true value. The true value being 0.1823. Now even then that's an approximation to the true. So actually we're not finding the percentage error, we're finding an approximation to the percentage error. And it's coming out as about 10%, which is actually quite high, but error, who cares? 9.7%. If the closer you get to x equal to 1, the smaller that error gets. And obviously you can see there's probably no great point going as far as x equal to 2, there's a massive error there. Okay. Now, what you could do, how could you improve this? If, as in class, I'd ask, how could you improve this? And if you want, you can stop the video and have a little bit of a think. You could just kind of copy the Euler method. That would be one option to estimate the log of 2. So what you do is you would, now the only thing, yeah, you could do it because log of x satisfies the differential equation dy dx is equal to 1 over x. So you can turn the function actually into a differential equation. So you could use Euler's method to do this. But what we need for the analysis of the error of Euler's method is a different approach. Is rather than using a tangent line, as this red thing is, we could use a tangent parabola. So we give it a bit of curve. Or you could use a tangent cubic tangent quartic, you could use whatever you want. These things where you have an x squared or maybe an x cubed or an x to the 4 are called polynomials. Now I have a little note there, more on this in MATH7021. You're not doing MATH7021, so I don't know what that's about. Anyway, so these polynomials, they're very easy for a calculator because they're just multiplication and addition. So if I write down a polynomial, so for example, in general, a polynomial is a constant plus a constant times x plus a constant times x squared plus a constant times x cubed, and you keep on going up to some final term, and this thing is called degree n. So this, if you just use this, you just be using a horizontal line to approximate the function, not very good. This thing will it'll give the line some slope. So if you take this is the tangent. And what this A2 will do, eventually we will see, is give a little bit of curve to it, so you get a parabola. And this will do a little bit more, it'll add a bit more, we'll just say curviness at this point. Okay. In general, you can approximate log using more and more polynomials. Like you go up to the power of 100, but they're all approximations. The question is it possible that so use the horizontal line to approximate log, that's not good. Use the tangent, we see it's not good. Maybe use the parabola. Now you might think the parabola works, but you could show in the end it doesn't quite do it. How about using this two? That's going to be a little bit better. How about use 4 of them? That's going to be a little bit better. What if you use 5 of them? That's better. 6 of them, 7 of them. And so you're going to have differences between these polynomials and log. There's always going to be a difference, but you can actually make the errors get smaller and smaller and smaller. And in fact, you can make the errors go to 0. But the problem is you have to take infinitely many of these, which seems like a problem. We'll write it down. So is it possible, for example, that log of x is not approximately, but equal to what you might call an infinite polynomial, which isn't a polynomial, but what you call a power series. So could log be equal to some constant plus some constant times x plus some constant times x squared plus ... that thing going on forever and ever and ever. Now I did this with my civil engineers last semester, and one of the students says, sure, that's impossible. You're adding up infinitely many things, you get infinity. Not so. Think about adding up 1 plus a half, that's 1 1/2, plus a quarter, that's 1 3/4, plus an 8, that's 1 7/8, plus a 16th, 1 15/16. So basically what I'm talking about here is you've got a box that's of length 2, and just keep jumping half the distance. 1 plus a half, plus a quarter, plus an 8, plus a 16th, plus a 1 over 32, plus a 1 over 64, and keep on going. As you take more and more jumps, you get closer and closer to 2, and you certainly don't go infinite. So this is possible. So to show you that it is actually, might be possible, is we've got something, a geometric series. So this thing says that 1 over 1 minus x is equal to 1 plus x squared plus x cubed plus x to the 4 plus ... Now the sum on the right goes on forever. Now you can get into kind of, you can bend your mind a little bit trying to understand this, but basically the way it works is the thing on the left is a number. Like say if you're talking about it, x equal to let's say for argument's sake a half. Thing on the left is a number. You put in x equal to a half on the left, you get 1 over 1 minus a half, that's 1 over a half, that's equal to 2. So x equal to a half, this is equal to 2. Now, it's difficult to add up infinitely many numbers, but the meaning of this and this together is that, okay, this thing is equal to 2, and you can get as close to 2 as you want, as long as you add up enough terms. So maybe you want to get within, you want it to be close to 2, or maybe equal to 2 to, whatever you want, 80 billion decimal places. Well, you can come up with, I won't do it because I'm not so sure how to do it exactly, you can come up with a number that if you add up enough of those and put in x equal to a half, that you will be equal to 2 to whatever, as I said, 17 billion or whatever decimal places. So it's exactly the case that no matter how close to this as you want, you can get that close by taking enough terms of the infinite polynomial, which actually we call a power series. Okay. So for example, using only 5 terms and putting x equal to 0.2 into it, if you put it into the left hand side, you get 1.25, and if you take 5 of the terms, you get 1.25 correct to maybe 1, 2, 3, 4, 5, 6 decimal places with only 5. If you want it to be correct to more, you just take more. Okay. So these infinite sums of powers are called power series. So we can write down, I'll write f of x equal to some constant plus some constant times x plus some constant times x squared plus some constant times x cubed, and then just keep on going. This is a power series. In general, these power series are only valid for certain values of x. This is nothing for us to worry about too much, but it's related to the fact that just like a function only looks like its tangent for a little while, some functions look like their power series just for a little while as well. So if you looked at the thing on the previous page, the 1 plus x squared plus x cubed plus x to the 4, if x is 2, this thing is finite, but this thing is getting bigger and bigger and bigger because you have 1 plus 2 plus 4 plus 8, but it doesn't work. That formula on the previous page only works when the absolute value of x is less than 1, strictly less than 1. Okay. So where are we at? So we're doing some theoretical background to analyze the errors in Euler's method. We're saying that functions like log of x, and it's going to come, we're going to see sine of x, cos of x, e to the x. You can approximate, or these are equal to what I call infinite power series. And what we're going to do is we're going to do approximations like the thing up here by not taking infinitely many terms, just finitely many terms. Okay. Right. So what have we got here? So Maclaurin series is doing this kind of regime, and I'm actually going to do it with sine of x here, I think, rather than doing it with an abstract thing. Yeah. We're going to do, say, let's look at a power series for sine of x, but let's do it for small values of x, in other words, x close to 0. That's what we're going to think about. So given a function f of x, now we're going to run with sine of x. So assume that sine of x is equal to a power series. So assume that sine of x is equal to a0, and that's a little bit dodgy in itself, but you're engineers, so we don't have to worry about it. So the problem is I have to find out all these values, a0, a1, a2, a3. It's kind of a nightmare. It's actually infinitely many problems. So how we get around this is we say that if these two things are truly to be equal, and there's a lot of work to be done here, that brushing under the carpet, that their values are equal at all values of x, and also if they're the same graph, their derivatives are the same. And their second derivatives and their third derivatives, etc. So what we're going to do is let's substitute into this thing x equal to 0. So we'll have sine of 0 is equal to a0 plus a 1 times 0 plus a 2 times 0 squared plus a 3 times 0 cubed. And now what I'm going to write, because it's useful, we've already mentioned it, is this is supposed to be this O. Everything after this is a multiple of x to the 4. X to the 4 is a4 times x to the 4, that's a multiple of x to the 4. Think about the thing with x to the 5, that's x times x to the 4, it's a multiple of x to the 4. So I can write everything after this is a multiple of, I could write, I'll do it up here. Plus everything after this point is a multiple, the order of x to the 4. Very good. So this is just saying that everything after here, there's loads and loads of terms, there's infinitely many, but they're all a multiple of x to the 4. Like if you have x to the 100 here, that's x to the 96 times x to the 4. So it's a multiple of x to the 4, it's order x to the 4. So after this we're going to put in x equals 0 to this as well.